Okay, good evening. So today we will see the final part. So before we have seen because the model whatever we have rendered or developed the machine learning model, it is having highest skew, so that we don't consider it as a ideal model. So for that, what we can do is we can go to change entirely model, like we can change linear model to logistic model or another different neural networks model or very high advanced models. But for now, we are not going into this first part. We will be transforming our data, and we will be trying whether our data will be a better approach. So let's go to our notebook. So yeah, so what we will try to transform is our price. What is our target column? We will be using uh, log function, transformation. So logarithms we will be using. So that's why mathematics is very important whenever we are doing machine learning, because we use different types of mathematical uh, equations or mathematical concepts. uh, because machine learning is all about implementing mathematics and programming into developing a model. So here, as we will be using displot again, just a challenge. KDE, we already know that the normal distribution. Uh, we have to calculate the skew of the distribution. We will be using a numpy's log function to, that is log prices, using displot and calculate the skew, which the skew closer to 0. Okay. Okay, first let's calculate skew. So we are just taking data price column, and we are calling skew method. Similar kind of we call a mean method also, the same thing we are calling. So now we are plotting our price, and using KDE equal to KDE, so you can give it true also, so it is also works. And we are plotting color equal to green, and we are just displaying in plot simple, just we are plotting Seaborn's plot using KDE, and we are displaying plot name as normal skew. Whatever we calculated, we are displaying here. We are giving a decimal point accuracy to 3. So here we have 1.1 skew. So if we have taken the same thing, so now what we are doing, we are using numpy logarithm function. We are applying to that date, like a price column, and we are plotting the same thing. Nothing we are doing. So we are plotting KD equal to, by default it will be blue. So logger price is Q, and we are displaying the same thing. So here if you see, there is nothing change. We are plotting the same thing, both are same. We are just plotting this. So here if you see, the skew is minus 0.3, so which is actually near to 0. So whenever our skew is near to 0, then only our whatever we are taking, whatever we are rendering the model will be an ideal model. So here we have seen the logarithm function is equal is did a better performance whenever we apply logarithms to our price. Yeah, so if you see the logger price, this makes a good candidate for our linear. Perhaps using the logger price it will improve Aspen models residuals. Yeah, now how does the log transformation work? So yeah, so whenever if there is a price equal to 7, then the logarithm when we apply, it is equal to 1.95. Whenever it is a 50,000, so then if a logarithm of 50 is 9.1. So here it is not very much a higher difference, but whenever we have seen here, so if you see, it's a 46.90 difference, but here it is just 5 difference. So we are actually, what we are doing, we are compressing, because of this what happens, there won't be any very much differences uh, on the estimation prices, so that we will have very less errors, like less residuals. I mean to say, because when we see the residual plot, so here we will be eliminating all these residuals, which are outliers we call it as, because that very much high difference won't be there. For the higher side, it will be very compressed, so that it will be fitting for our purpose. So if you see, we can see, so just we are plotting data price, scatter plot, and logarithmic data price. So it's again same title we are giving, y label, x label, and plot. So if you see here, this is actually a logarithmic plot. So if you remember from our lower classes, the logarithm is something. Uh, the logarithm values will be, whenever we plot logarithmic values, it will be exactly resembles like this. So now, because higher values will tend to have lesser values, so that's why whenever we go to higher value, it will be don't go in a straight line, but it will be come closer to the actual value. So now let's develop another model. As of now, if you see, before model we haven't used logarithmic, but here we are using a logarithmic price and all the dependent variables. Again, we will be doing the same thing. We split our data, we train our data, and then we will see how our model performs depending on our uh, logarithmic data. So here the new target is, so the features will be the same. So we are dropping the price column here. Just we are applying a numpy's logarithm function to total price column, so that it automatically converts all the price column values to logarithmic values. And then again the same thing, we have split it into four variables: the features, new target, here text size we are giving 0.2, here random set is 10. Whatever we have developed for before model, the same thing. So here we are taking another new variable, logarithm regression. So we are using log underscore regression equal to new, we are creating a new linear regression object. So then we are fitting our x train data and here y train data. So just because our train data is a logarithmic data, we are given our variable name as, so we can give any variable, but for our reference purpose we are giving log underscore y. Now we are calculating the r square score also. So here the predictions equal to again predictions, so residuals equal to residuals. So if you see here, let's run this. So we just it's a difference of variables. If we carefully observe, we just changed the variables. There is no change in method types. So the predict method is the same, and we are just train data minus predictions, which will give the predictions. So here our r squared error is 0.79. It's very much better because before we have a 0.75 only, but now whenever we give logarithmic values, logarithm price values, our r square got increased to 0.79. So the same thing, so we will see how whenever we have given logarithmic values, how our coefficients behave also. So now if you see, the coefficients also changed very much. So it's in the case of minus 0.0, 0.00. So but if you see the old coefficients, the normal regression without using coefficients, so it is very high in number. So 16, some 3. something. But here if you see, whenever we are giving the coefficients values drop it to very much low, like 0.7. So which is a good sign actually. So now, yeah, so we have to carefully observe the sign. So the key thing we look for this till the sign being close to zero results in higher property prices, because CH is a higher coefficient greater than 0. Yeah. So if you see, yeah, the apartments near to child river will have highest property prices. Yeah. So Peter ratio, parent, like pupil to teacher ratio is a clearly negative again here. Smaller classroom sizes are indicative of higher quality education, so I have negative coefficient. Now this is again nothing but we are just plotting actual graph of actual versus predicted log prices, and this is the same thing we already did, but here uh, we are plotting log predictions and predicted values, which we already done. So just for our reference purpose we are plotting it, so nothing changing. So just the y log and the titles will be changing from above. So if you see actual versus predicted, so our line is actually near to our all the data points. So but if you see which is not, r squared is 0.075 and r squared is 0.79. Log prices when it is a log prices, when it is normal prices. So our linear regression line is very much, the outliers are very much away from our linear regression line, and the concentration also. But here if you see, the concentration and data points is very much near to our linear regression line. So again residuals versus fitted values when it is for logarithmic. So we have more concentrated values which is under 3.75, but here there is a very scattered values. Yeah, obviously because it is very hard to distinguish obviously, but the predicted values seem to be closer, right? So they seem to be closer to our predicted line, but obviously it is very hard to distinguish. Obviously it is not helpful. So what we will be doing, we will be calculating a skew and mean, which we already did for before model also. The model is uh, regression, REGR is one model, and we have logarithmic regression, the other model, and we are just again doing the same thing, nothing differs. We are using that models. So here we are again rounding off residuals to mean to 2 decimal points, again skew to 2 decimal points. We are plotting it, this plot. So we are plotting side by side, like again if you see log residuals kd equal to true, and indigo navy the same thing is log price model and original price model. So if you see here, it's a skew of 0.09, which is very much lesser than uh, the original model, which is 1.46. So we can clearly observe the difference also. So it is very near to our normal distribution. And mean is obviously it's again 0 obviously. So we have improved our model by using logarithms, because we have improved r squared value, and even the skew also we have reduced. to 0.09, which is very near to 0. So the ideal model would be 0.0, but it is very not in, we can say it is a very little chance of getting a 0.0 skew. So yeah, it is very much near. So our model performance is really increased. Now we will be testing our two models. So using now the real test is now whenever we have given the other test data. So we have splitted our data right now. Whenever the model is not seen the data which it is on trained, so we are giving a test data and we are calculating r square numbers. So whenever we do this, so now it whenever we give that test data, it drop it to 0.67. Our original model is 0.75. Now it dropped to 0.67. But our logarithmic model is 0.79, which is dropped to 0.74. Yeah. Yeah, because by definition r square should be actually near to 1, so then only our model will be very much useful. But we have a good model actually for now. For our learning purpose we have already done. So this is nothing but predicting property values using regression coefficients, which is already we have seen. So we are just starting point average values. So what we are doing, we are dropping the price features and we are doing the mean of the all the column values, and then actually what we are doing, we are doing the transpose all the values average values, and we are just creating a data frame of that all the average values of that columns. So if you see all these average values generally. So now the log price estimate, what is the dollar estimate you will do. So okay, so now we have to predict because now we have different because we have finally built a model, right? Now we have to predict what is the price depending on various factors. So here what we are doing, we are taking only one property status. We are taking the first column, like I meant to say, the first index of all this because all these are dependent variables, right? Because the price is equal to theta plus theta 1 plus of theta 2 of nox plus all these dependent variables. We are giving that as input and we are giving what is the price estimate. So then we are doing a logarithm e power because in Python it is a e power logarithm estimate whatever we come logarithm. So whenever we want to convert into normal value, so we should multiply with e power. So again the exponential we call it as into 1000. Yeah, so whenever we run it, yeah, so for the average all the average values the logarithm property is $3.3, but whenever we convert into dollar estimate it's 20,000. So now the final part is like this one. So for example, if we have next door neighbor is true and there are number of rooms equal to 8 and number students per class equal to 20, distance to town is 5, and pollution equal to some they have given quantile, and amount of property also quantile very low. So here what we are setting is we are setting the property status this one row to a number of rooms, people to tuition ratio students per room is 20, property status. So whenever if next to ever it is given as true, so if next is like it is just equal to true, so then we are setting it to 1, otherwise it's setting it to 0. NOx is the pollution. So these all are property characteristics. So yeah, property status, amount of poverty. So we are setting up all this data on this property status data frame, and we are passing the property status data frame the first row, because it is having only first row, right? Because the index is 0. Yeah. So logarithmic estimate and again e power. So the same thing. So this is how we generally built a machine learning model. On top of that, different variables, because there are around 13 variables, so that we have passed different variables such that it actually estimated the property, like the price of the house in logarithmic, and we are actually converting that logarithmic estimate to dollar estimate. Sorry, I have to run this. First I have to run this, and then this, because we are setting it up, and we are setting this up. So it is like 25,000, around 25,000, depending on different factors. Yeah, yeah. This is all about how we build a machine learning model using different variables and different log. We have used logarithmic techniques, but we have used only linear regression model in this course. So you can explore different models for different predictions depending on our whatever the data we are available. So depending on how much data and how much times you train machine our model, and depending on different algorithms, and depending on r square number and skew, the skew should be low and r square should be high. So all those factors, our machine learning model will be very accurate. So but it will take time to build such models. So yeah, but it is worth to start with simple linear regression model, so that you can check. Yeah, that's it. We are done with the linear machine learning also in this course. Yeah, thank you.